All right, guys. So this course is allocated for dislocations in BCC materials. So BCC materials, when I say BCC, please think very, very brittle materials, hard and brittle materials. And this course, we will see the main reason why BCCs are strong materials, but brittle materials. Mostly, we have another class for martensites. Martensites are more brittle and strong, but BCCs are also strong and brittle materials. So, do you guys remember in FCC, how many crystal systems we have?
12 hocam.
12 crystal systems, right? How about for BCC? BCC, we have one big atom in the middle at the body and 1/8 atoms at each corner. So Berger's vector, the slip direction is always 1, 1, 1. If you look at these planes and directions, the direction is always 1, 1, 1 direction. But we have 3 different planes. 1, 1, 0 plane, which is this guy right here. 2, 1, 1 plane, which is this guy right here. And 3, 2, 1 plane, which is the green guy right here. So in total, we have 48 slip system. Combination of all these slip planes and directions. And if you remember FCC, we have a dislocation, but they separated like the Shockley partials or Frank partials. And the main reason is the stack and fold energy is pretty low. So for energetic reasons, we see the separation. But for BCC materials, the stack and fold energy is relatively high. It's very high, so that we don't easily see the separation of dislocations. So, and once you check the atomic packing factor, BCC is 68% atomic packing factor. So BCC is not closed packed instead of FCC, which is closed pack system. BCC crystal structure is not closed pack. So one question. For FCC, we have 12 slip system. For BCC, we have 48 slip system. Why do you think FCC is more ductile than BCC? Like for BCC, we have more slip systems. If you compare just the numbers, you would expect BCC should be more ductile than FCC. But instead, we see that FCC is way more ductile than BCC. Quickly draw representation. Sigma, epsilon. FCC, we have a little bit elasticity, then we have lots of edge dislocation motion and lots of plasticity. For BCC, we have hard material and it's less ductile. For martensites, BCT, body-centered tetragonal, it's mostly very limited ductility plasticity. Basically, the main reason, first, it is not closed pack. The second, we don't necessarily need more slip systems. Actually, 3 or 4 slip system is more than enough. So 48 slip system doesn't mean that we have more plasticity. We generally need 3 or 4 slip system, like the direction and the plane, where the dislocation use this planes. Instead, we need some dislocation activation and dislocation motion. For in BCC, it is really hard to activate these dislocations because BCCs are mainly deformed by screw dislocations, and we need some thermal activations. We need to overcome the energy barrier to activate these dislocations. But for FCC, we have edge dislocation, which is carried by phonon drag, phonon activation, and phonon activation is athermal. We don't need any thermal activation to activate phonons and edge dislocations. All right. Sorry. Annotate, clear all my drawings. Okay. So BCC is not closed pack, and slip occurs always in 111 plane. So in FCC, which plane is the slip plane? For FCC, the slip plane, which plane is the slip plane in FCC? Anyone? Khan, do you remember the slip plane in FCC?
Actually, Hocam, I don't remember.
Try to remember the slip plane in FCC. Always 111, right, Ramazan? Thank you. FCC, the slip plane is 111. BCC, the slip plane, always 110. And it has the highest atomic density. So if you check, so we said we have 3 different planes, 110, 211, 311. For 110, 111 direction, in total we have 12 slip system. For 211, 111, Berger's vector is always along 111 direction. We have 12 slip system. For 3 to 1 plane and 111 direction, we have 24 slip system, including the pencil glides. In total, we have 48 slip systems. So once you compare edge and screw, the core energy of screw is extremely low because we have compact core in BCC. Instead, for FCC, it is planar core. And yeah, there is a strong asymmetry in terms of properties between screw dislocation and edge dislocation. Core energy of screw is very low in BCC materials. So total energy is the line energy, dislocation energy, like the elastic energy, plus the core energy. Since the core energy is very low in BCC, screw is the dominant dislocation. It's energetically favorable dislocation over edge dislocation in BCC. It's easier. So always the nature goes to minimum energy, maximum entropy. That's why BCC materials prefer the activation of screw dislocation. Edge dislocation, they just disappear. They just disappear shortly after very low amount of plastic deformation. they just disappear due to some energetic regions. They dissociate into Shockley partials, Frank partials, but for high stresses and like thermal activation, we activate the screw dislocations. And on contrary to edge dislocation, this is very important. Screw dislocation have very high lattice resistance, and their motion is thermally activated. Edge dislocation is athermal, but screw dislocation, we have thermal activation. So this is one screw dislocation. We have these kind of kink formations. We have different energy states, and they form kinks and activates. Okay, so screw dislocation core is non-planar. It is compact core. It has a triangular shape, and it is very compact, hard to activate this dislocation. It is not planar, and it is very hard to move this compact core, which results the high lattice resistance. For example, this is one screw dislocation, and you see the compact core of screw dislocation. Again, compact core of screw dislocation. So how we move this screw dislocation? Basically, we have energy levels, and the dislocation just stay. Let me draw another schematic though. Let me just stop sharing this part and draw another schematic. So for screw dislocation in BCC, which plane is the slip plane? We just covered it. What is the slip plane?
110.
Perfect. Slip plane is 110. Sorry, actually we can have different planes, but the direction, right? We can have actually like 110 plane, 211 plane, 321 plane, but the direction always and always 111 direction. Okay, let's consider 110 plane. And the direction, let's say always 1, 1, 1. We have different energy states. Let me draw such a just any representation of energy state. All right. So let's say our screw dislocation is here. So they can locate at discrete energy states. So this is one energy level. These are all different energy levels. And this dislocation, screw dislocation, wanna jump from this energy state to this energy state, the lower energy state. Its core is compact core, not planar core. So it is really hard to activate the motion of this screw dislocation. You just increase stress again and again constantly till maybe 400 megapascals, 500 megapascals, and with thermal activation, you firstly activate the middle part of this screw dislocation. So this middle part will go to the top So it will have something like this. And suppose you don't see this part, then this part goes to the lower energy state. You form this kink, what we call it as kink, and this part goes to the lower energy state. Then the rest will start to evolve at the higher energy level. Then they move to other energy state. Then we kind of create the kink formation. So these are just edge parts of the screw dislocation. Then this is the screw part again. And this dislocation evolves, and they move to the lower energy state. These parts are called kinks. And kink, let me write kink. Basically, the movement of screw dislocation is thermally activated and with kink formations. We generally see kink formation with edge components, then they move to other energy states. So in this PowerPoint, so in this PDF, you see better representation of energy states. So our dislocation will want to move from one energy state to lower energy state, but we need some thermal activation because the core is the screw core is not planar, compact, and we have high lattice friction in BCC materials. So here you can see better representation of kink. So our initial dislocation is at A, and the dislocation wants to go lower energy states. Firstly, it creates the edge parts, which are, let me try to annotate. These are the edge components. Then we have kink formation here. Then this kink goes to the lower energy state. Then we have this part goes to this energy state. These are all kink formations. And at the end, our screw dislocation will come to lower energy state. So this formation is called as kink pair nucleation. And we generally observe this nucleation via experiments, but it's not suitable for study with molecular dynamic simulations or other atomistic techniques. All right, so we have a formula. This is the speed, and this is the energy barrier that it needs to overcome. So the energy barrier it needs to overcome is this energy. And just the velocity. Basically, it is just delta E minus temperature, energy, and temperature times the entropy. All right. Another representation of compact core of screw dislocation. They are at rest, and once you glide your screw dislocation, you form the kinks. Then the kinks go to the other energy state. Then the rest of the dislocation will go to the other energy state and complete the formation of whole dislocation, whole screw dislocation. Don't forget, while forming these kinks, we have edge components too. Perfect. We have Berger's vector is always 1, 1, 1. And this is the 1, 1, 1 zone. So this is very good slide. The evaluation governed by two mechanisms. One, the dislocation moves forward the nucleation and propagation of kinks. So this is the kink pair nucleation. We have edge parts, and screw parts. You cannot move the whole screw dislocation to other energy state. It's energetically not feasible. Instead, you create the kink and the formation of whole dislocation in the other energy state is step-by-step formation. Kink nucleation, kink pair nucleation, then kink pair propagation. Here we have only one kink pair, more kink pair propagation, then whole dislocation, screw dislocation go to the other energy state, go to the other red dot. So, sorry, these are animations, but I cannot. I have the videos of these animations. I can send these animations to you. All right, I'll just skip this. Activation volume, flow stress slides, because these are kind of the slides where we gonna focus on after I explain the Martin side. All right, so for 1, 1, 1 plane, we have more flow stress. The critical shear stress is greater along 1, 1, 1 plane. For 1, 2, 2, 1, 1, 2 plane, we have less critical result shear stress. So this is the excess stress for different planes. And for 1, 1, 2 slip, 1, 1, 2 plane, after the critical band and the temperature, we have very, very low excess stress, and we can activate the dislocation after certain amount of temperature very easily. So for low temperature, the critical result shear stress is high. That is why it's hard to activate this screw dislocation. But at stage 1, at high temperature, it's easier to activate the screw dislocation. Of course, for BCC, we have tension, compression, asymmetry. What I mean by that is, also annotate. Under tension, we have elasticity and plasticity, but for compression, the tensile strength under compression is greater than the tensile stress under tension. So this is sigma tensile stress UTS under tension and sigma TS under compression. This guy is greater than this guy. And there is a homework that, so mechanism actually, you can answer right away, but I want you to focus more why we have tension, compression, asymmetry in BCC materials, and why the tensile strength under compression is greater than tensile strength under tension. So this is your second homework. You just need to write maybe 1 page, maybe even half page, or yeah, maybe 1 page is good. Just try to discuss why we have this asymmetry and the tensile strength under compression is greater than tensile strength under tension. All right. That is why I don't want to mention twinning and twinning asymmetry. Perfect. Impact test. Basically, to calculate the fracture properties of materials, we don't do, like we do, of course, tensile test, compression test, but mostly impact test. We have an impact hammer, which has a potential energy. We release the hammer and we put specimen and we fix the end of specimen, and this potential energy of the hammer will be delivered to the Sharpie impact specimen, which has a pre-existing notch to create the localized deformation and localized strain. So we will have some crack formation here. Crack will propagate along the notch, and the specimen will absorb some of the energy, then fracture. Then we will read the impact energy that the specimen can absorb and determine the ductile to brittle transition temperature. For BCC, in BCC materials, we obtain a sharp change from ductile to brittle after critical temperature. And that temperature is called as ductile to brittle transition temperature. So you conduct your impact test at different temperatures and you just record the impact energy. For BCC materials, you observe a drastic change. So this region is ductile region, and after the critical temperature, you observe ductile behavior, but for critical temperature, you observe brittle behavior. That is why actually BCC materials are deformed mainly by screw dislocations. So at high temperature, you can activate your screw dislocations because it's like thermally activated. The motion of screw dislocation is thermally activated, but at low temperature, you cannot activate these screw dislocations. So at low temperature, they are brittle, but after certain point, they are ductile. That is why for BCC metals, we have a distinct ductile to brittle transition temperature, but for FCC, they're mostly deformed with edge dislocation, and it is a thermal process, and we don't see any critical ductile to brittle transition temperature or for high strength steels. Actually, that is the main reason why we saw failure in the giant ship Titanic. It's an engineering disaster. It's an engineering failure. Basically, the engineers design the materials for room temperature and for hot temperatures. They didn't care about the low temperature. They didn't conduct experiments at low temperature. They thought the material gonna be ductile. But once the ship hit the iceberg temperature is below the ductile to brittle transition temperature. That is why all the bolts and other materials which are BCC crystal structure, which were BCC crystal structure, they behave brittly. So they just failed without any significant plastic deformation. Like the giant ship, Titanic, the material, the hull plate, or ASTM 36, they are brittle. And once it hit the iceberg, you see before 0, it is brittle. So around -50, you don't carry too much load. Your material is brittle, but mostly they tested these materials at room temperature or high temperatures, and they thought the material gonna be ductile, but once they hit the iceberg, they behave brittle, and they just, boom, disappear. So we have a separate lecture for crystal plasticity. It is the method, like a simulation method we use, or like a theory. I'll explain the theory for another class. And for this class, I'll stop at this point. Is there any question that you want to ask about the screw dislocation and BCC materials?
Not at the moment.
Then I'll stop at this point.